Welcome to Lecture 12A in MOL200. My name is Aurelia Lewis. I'm an Associate Professor at the Department of Biological Sciences, and today we'll focus our lecture on lipids, in particular in fatty acids and triacylglycerides or TAG and their general properties. Here are the source from the Leninger textbook and the page numbers you should focus on for this chapter. We will focus on fatty acids, as I said, as they form important storage of energy. But if you're interested in lipids in general and how they can be altered in disease, we have a course, MOL210, and we will look at the structure and properties of membrane lipids and the signaling in health and disease. But now we look at lipids because they are one of the four main molecular blocks of life, or building blocks. And these fatty acids are the unit of these building blocks. They can form more larger units of lipids as fats. So these are tags, triacylglycerides, lipids in membrane, but other types of lipids. But these molecules are important in metabolic pathways in health and disease, and they are at the standard stage of disease such as insulin resistance, obesity, metabolic syndrome, diabetes, and cancer. So these molecules are extremely important to know more about. So lipids, if we go back first to generally about lipids, it's a family of structurally very diverse class of molecules. And here on this slides are some examples of these very different types of lipids. You can see here a presentation of a fatty acid. This is the 1-triacylglycerol. So we'll focus this lecture on these two lipids. But fatty acids, as I said, are integral part of tags, but also of membrane lipids. This is an example here of a sphingolipids carrying a fatty acid here. But you have other types of lipids such as cholesterol, and you can see this structure is very fundamentally very different to these first lipids. But also they can be varied forms of these isoprene unit that you can see here in these separated by these lines, dotted lines, and this is the representation of one particular molecule, the coenzyme Q, which is part of the electron carrier in the mitochondrium that you may have heard about from previous lectures in this course. So overall, these lipids are of various diverse structure, but their main definition is that they are organic molecules and they are characterized by very low solubility in water. This means that, in other words, they are relatively hydrophobic. They're more or less depending on the different types of lipids that we have here. So the lipids have a variety of functions in life, and they can be used as storage of energy, and we'll focus our efforts on this, but they can be important for insulation from the environment. They are water repellent because of their hydrophobic nature. They can also give buoyancy, especially for marine mammals, and many more. But lipids in general are classified because of their diverse nature. They're classified in two major categories according to their structure. So there are lipids that contain fatty acids, and they can be quite complex. And these can be further separated into two: storage lipids and membrane lipids. As you can see here on this diagram, these are storage lipids, where you can see 3 fatty acids are esterified on the glycerol backbone. But fatty acids also can be found esterified in membrane lipids of different nature. And you have another category of lipids which do not contain fatty acids, and these would be cholesterol, as I showed earlier. These isoprene type molecules. They can be vitamins, those are hydrophobic vitamins, pigments, etc. Let's focus now on fatty acids. So what are fatty acids? These are carboxylic acids. You can see here there's an example, or two examples of 2 fatty acids. And they are carboxylic acids because they have a carboxyl group here, which gives their acidic properties. And it consists also of a hydrocarbon chain made of carbons containing between 4 and 36 carbons. Now, almost all natural fatty acids have an even number of carbons, and this is because of how they are synthesized and how they are catabolized, which we'll go into the next lectures. And most of them are unbranched as well. So you can find them fully saturated, just like this one here. And that means that there are no double bonds between the carbons in the chain. Or they can be monosaturated, and here is an example here. There is one double bond here in the hydrocarbon chain, and which gives different properties to saturated fatty acids. In addition, you can have polyunsaturated fatty acid. That means that they have more than one double bond in the hydrocarbon chain. But we'll show some example in a minute. So there are some clear nomenclature of how to design or how to describe these fatty acids, and they can have a systematic name. For example, for this particular fatty acid, it's a cis-9 octadecanoic acid. Cis because there is one double bond here in position 9 and carbon 9 if you start counting from the carboxyl group. So this is carbon number 1, and here at carbon number 9 we have a double bond. It is in the cis conformation, so you would have hydrogen here if they would be marked. So this is the systematic name, but they've been also named depending on how they've been identified or in which source they are very rich in, and this particular one is called oleic acid. So, as I said, in the numbering of the unsaturated bond, there is a delta numbering from the carboxyl group, and that will describe where this first double bond exists, so between carbon 9 and carbon 10. But there is another way of numbering, especially long fatty acids, and this is called the omega numbering, and you will know, you would have heard about it, about omega-3 and omega-6, for example, fatty acids. This one is an omega-9, but that is because we start numbering the carbon from the other ends, from the methyl end of the fatty acid. And this time, so this is an omega-9 because this is carbon 1, omega-1, and this would be carbon number 9 of this fatty acid. This is an important way of numbering because of certain long polyunsaturated fatty acids that have important properties in our health, such as omega-3 versus omega-6. Here are here is a table of some commonly occurring fatty acids. These are saturated. These are all saturated fatty acids. You can see that there is 0 double bond here. All of them are saturated. So one of them that is very important to learn is palmitic acid. And you can see that depending on of their length of the hydrocarbon chain, i.e. the number of carbons, you can see that there are different physical properties for these molecules, including their solubility and their melting point. And you can see that it increases, the melting point increases as the length of the hydrocarbon chain increases. That's because it takes more heat, more energy to dissociate these molecules from each other and to change their state. Here is a table of monounsaturated or polyunsaturated fatty acids. And you can see their systematic names again and their common names. So here is our palmitoleic acid, which has 1 double bond. So it's a palmitic acid with a double bond. And now you can actually see that the melting point is a lot lower for these these fatty acids as soon as there is one double bond in their chain. These are in configuration cis for the double bond here. This is the configuration that is biologically normal to have. Now, certain fatty acids, as I said, are called omega-3, and these are essential nutrients for us. So as humans, we need them because we cannot synthesize them, but they are extremely important for our health. And they include, for example, alpha-linoleic acid, dogexohexanoic acid, and eicosapentaenoic acid, EPA, DHA, or ALA for short. These are 2 examples, a monounsaturated and a polyunsaturated. So this one has EPA has 5 double bonds, and as you can see in the omega numbering, we find the first double bond here in the 3rd carbon from the omega end, i.e. the methyl end. So this is an omega-3 type fatty acid compared to this one, which is an omega-9. Now, the conformation of fatty acids is different whether this is completely saturated or unsaturated. And the double bond will, which is in cis conformation, will actually induce a kink, i.e. Here a change in the orientation of the hydrocarbon chain. And this means that completely saturated fatty acids tend to have a linear conformation, and that means that these hydrocarbon chain can pack well together, and they have a lot more stable interaction between these hydrocarbon chain. In terms of unsaturated fatty acids here, if these were to pack together, for example in membrane, you can see that they are disordered and more fluid, and hence less stable. So this will mean that it will require less energy to change the state of these molecules and disturb their organization, and hence they will have a lower melting point. These are examples of some occurring fats that you have in your kitchen. So olive oil, for example, which is liquid, because if you look at the proportion of the unsaturated fatty acid compared to saturated fatty acids, there is a high proportion of these especially monounsaturated fatty acids. So at room temperature or in your kitchen, olive oil will be liquid, whereas butter, which is a soft solid, in your fridge it will be completely solid, but because of the higher proportion of saturated fatty acid. But if you leave it on the counter in your kitchen, it will start to be less solid, and of course if you cook it, then it will change state to a liquid form. Whereas if you look at beef fat, which has an even more proportion of saturated fatty acid, this is it is a hard, solid type of fat. So overall, the solubility of these fatty acids will decrease as the chain length increases. There will be a lot more difficult to solubilize. And their melting point will decrease as the chain length decreases. So the shorter they are, the lower the melting point. And on top of it, the melting point will decrease as the number of double bonds increase in their hydrocarbon chain. Now, there is, as I said, so the naturally occurring fatty acids are in cis conformation, as you can see here. Hence the kink created in the hydrocarbon chain, whereas trans fatty acids, which are not naturally occurring, have this configuration, and this means that they will resemble more of a linear type hydrocarbon chain, just like saturated fatty acid, even though they have a double bond. So these trans fatty acids are formed due to partial dehydrogenation of unsaturated fatty acids. So this is done by transforming food and to allow an increase in shelf life for certain fat and certain oils, especially that will solidify these oils. So then this trans double bond will linearize and extend the conformation of a hydrocarbon chain. So then this means that these trans fatty acids, which contains unsaturated fatty acids, they can actually pack more regularly, just like you would have saturated fatty acids, because of the position of the conformation of this double bond. So they will have higher melting points than the corresponding cis form of these unsaturated fatty acids. So consuming highly transformed food with containing trans fat is actually detrimental for health, and it's been shown to increase risk of cardiovascular disease. So these fatty acids are integrated from the diet in our membrane and our cell membranes, and this will decrease the fluidity of membranes and have a detrimental effect at the cellular level and at the tissue level, and therefore at the organism level. So avoid eating very transformed food. So we've looked into focus on our fatty acids and the general properties. Fatty acids are actually found in many more complex lipids, including these storage lipids, which are triacyl glycerols. This is one of the categories. There are several categories of lipids here that are classified here, and these tags belong to glycerol lipids. So fatty acids are found in triacylglycerol. So this is the major form of storage energy. And they can be found in the form of solids or liquids, depending on the type of fatty acids that are esterified in these molecules. So if you have saturated fatty acids, they will be more solid, and if you have unsaturated, they'll be more liquid. So these molecules are extremely hydrophobic, and we can see this in this molecule. So this is a triacylglycerol, and as its name says, it's tri. There's 3 fatty acids esterified into a glycerol backbone molecule. So this is our glycerol here, and each of the hydroxyl group are esterified through the carboxyl group of 3 different fatty acids in this case. So this is a mixed triacylglycerol in this example. And these tags, which are extremely hydrophobic, so they are not soluble, are stored within in our body in these in adipocytes. So these are cells of which have the main job is to store these very hydrophobic molecules, and this is a section of an adipose tissue, and each of these are different cells, different adipocytes, and they are completely white, translucent, because they are full of these molecules. So fats or tags provide efficient energy, and it is a very efficient way of storing fuel. And they have a lot more advantages compared to polysaccharides, for example, glycogen, because they carry more energy per carbon. Because they are more reduced. They carry less water because they are completely hydrophobic compared to polysaccharides. So fats or triacylglycerols are used for long-term energy needs. So it's a good storage source of energy, but it has the disadvantage of being slow in delivery. But fortunately, we have another source of energy, which is fast, and it's important for short-term, for quick delivery of energy, which is such glucose and glycogen as the polymer. Here is a slide on waxes. This is not part of pensum, but these are also important lipids to hear about. And they are esters of fatty acids. There is an example here, so you can see this is a palmitic acid that's esterified with a long chain alcohol, which is called 1-triocontanol. So this is a wax, and they form very different types of structures. For example, this is the beeswax. Useful for bees to store the honey, but there are many other types of functions that you can look into more if you're interested. But this is the end of this first lecture on the properties of fatty acids, and then the next following parts will be on the biosynthesis of fatty acids and their catabolism.